Hey everyone, today we are going to continue our explorations of the topic of data mining. And now all the caveats that I laid out at the start of the multilinear regression subject still hold, but here we want to talk about the ideas of classification of data. So this is using data mining techniques to kind of sort your data into categories. And the method that, or the data set that I'm going to use to explore this is from the Sloan Digital Sky Survey, one of the original large area surveys of astronomical data from the sky. The data that I'm going to be using is going to be basically drawn from imaging data in the sky. And what they did is they have this giant camera here that they put on the back end of a telescope, and they pointed it at the sky, and they let the sky track overhead, and then you can sort of see these things have different colors here. So each of these banks here represents five different cameras, and they have five different colored filters in front of them, and they let a star track across here, and they kind of read out the detectors at the sidereal rate of the Earth's rotation. So you kind of march across and measure the light from objects as they sort of move across the sky in these five different filters here. And this was the first really massive digital survey of large areas of the sky, and they covered a big chunk out here. This is a Hammer-Atoff projection of the sky, and this is kind of the region where they did their observations. And so they measured bunches and bunches of objects in the sky and measured their light in five different bands. And just a little astronomy lingo so that we understand the data set that we're working with. This is the five different bands here are called U, G, R, I, and Z, or UGRIZ is the name of the filters. These are the throughputs of the filters, and so the U filter basically passes light around 350 nanometers. The G filter passes light around 500 nanometers, and 600, 750, and then out here at 850 or 900 for the Z filter. So this represents basically measuring the amount of light from different parts of the optical spectrum. The other thing to remember is that astronomers use a backwards logarithmic brightness scale called the magnitude scale. And so everything that I'm presenting here is going to be in these magnitude units, which is negative 2.5 log base 10 of the flux plus some coefficient. And this is just set up so that small numbers like 1 are brighter objects than larger numbers like 5. And this is designed to be back compatible with a system used by the ancient Greeks because, yeah, I don't know. Still unclear. Anyways, we're measuring the band magnitudes of a bunch of different objects. And when we look out in the sky, we basically see two types of objects in the Sloan Digital Sky Survey, first order. And those are galaxies and stars. And astronomers like to make this color magnitude diagram. And in terms of the magnitudes, these are G-band observed magnitudes on the y-axis and G minus R on the x. And the sense of this diagram is that there's bright objects are at the top, faint objects are at the bottom, blue objects are on the left, and red objects are on the right. So short wavelength light objects go onto the left side, long wavelength dominated objects go onto the right side. And what's neat about this is we can sort of sort out this into two different categories of objects, galaxies and stars. And I'm actually using the Sloan Digital Sky Survey categories of these, and they measured these morphologically. So it's a camera, and if it's sort of extended and fuzzy, that's a galaxy. And if it's a bright compact source, that's a star. So they have these classifications embedded in their database, and you can sort of see the stars form this nice kind of, has this sort of two spike feature, or two vertical stripes in the space, and then galaxies are intermediate between these. As diagonal lines, a selection effect, And these two spikes here are sort of representing different stages of stellar evolution. And the galaxies are kind of in the middle and all over because they're mixes of a bunch of different stars. So it's kind of the vector average of these objects here. So this gives us a sense of kind of where those data are in this data space of these kind of two colors and magnitudes. And what we want to do is use this information and see how well we can make a prediction based on the colors of light alone, whether this is a star or a galaxy. So we're basically using information to get the Sloan Digital Sky Survey people used imaging information, which we're going to pretend like we don't know, and we're going to see if we can make predictions about whether something is a galaxy or a star just based on this color. And this should be hard. These things don't kind of line up too well. So I want to talk a bit about we do that. So one way of doing this is this thing that's called a decision tree. So we're going to pretend we know some subset of the data. And this is kind of an auto-generated flowchart for deciding whether something is a star or a galaxy. And so we take this complicated sample space, which represents all the different fluxes, and I've also added in their ratios, the flux ratios, which are just differences in logarithmic space. And so I make this large dimensional data set that is representing these 5 different colors, and I ask, well, some of those I know are stars and galaxies, and we're going to divide the sample space into a bunch of different regions. So it ends up being, I think I ended up with 11 different data dimensions. So we're just going to slice that up into kind of partitions of the data. So we draw a line in one of the axes that sort of sorts it into larger than that line or smaller than a line. And we're going to pick which of those partitions lead to the best sample separation between the stars and the galaxies. Which of these sort of randomly chosen dividing lines are the ones that actually separate this? And this is called a decision tree. We're going to use as our goodness of fit something called the Gini index, which is basically the sum of the proportion of training data in a region that belongs to the kth class times 1 minus the training fraction that belongs to not the kth class. And so if we have a good partition of the data, everything will be either zeros on one side and ones on the other, or stars on one side and galaxies on the other. And so this Gini coefficient is going to become 0 because it's either 0 or 1, and then this term is going to be 0 if the inputs are 0 or 1. So we want that Gini coefficient to be small, given a good, pure samples without much contamination from the other population. And we can stick in here and we use the sklearn method. We say, I want a decision tree classifier, and I'm going to take some of my data set. So I ended up sort of splitting out 40% of the data as testing data, and I use 60% of the data to train the model. And I say, okay, well, there's max depth. I'm going to put a random seed in here, and I'm going to fit the training data. And then I want to test how well the test data, so that's the 40% of data that are retained as sort of held back as testing, how did the decision tree classifier do on those data, and then how well did it do on the original training data? And this score is the number of correct classifications over all classifications, so it gets a 77%. That's pretty good for just randomly dividing up a data space. And you can actually go through and visualize what this tree looks like. That's one of the functions of the decision tree methods in Python. And it'll just spit out a nice little graph that looks like this. And you can see how it's doing the division. which is it basically takes the Z magnitudes and says, okay, is it less than or equal to 18.68? That leads to a Gini coefficient of 0.39 on 195,000 samples that I was doing the testing on. And then it says, okay, if it fails, let's see here, if it fails that, I guess if it passes that, it goes down this node. And if it fails that, it goes over here and is a galaxy. And then this method does a difference between the R and the I coefficient, which leads to this Gini coefficient on this many samples. And you'll notice that this 195,000, 27,000 go over here and are classed as stars. And then 168,000 that come over here from here as galaxies. And then it says use this RI difference to basically split up that sample. And you can see that the Gini coefficients sort of start to split into galaxies and stars. And this uses a different cut, and it says, okay, then I figure out whether I'm galaxies or stars. So this starts to split up the data set, and it tells you how many are flowing through each branch of the tree. Now, if you go back and you look at my code, you'll notice that I've just picked a max depth of 2. I could go and pick a max depth of 3 and regenerate the tree. And you'll notice that, again, it uses, you might not be able to read it, but it says Z raw as my first decision point, then RI or R minus I colors as my second decision point, and then this uses IZ and GR as my next decision point. And so this divides this up here. And so I can make a deeper and deeper tree and put more and more classifications. And it should do a better job as I get more and more refined. And what we can do is we can actually plot the scores for the testing and the training data as a function of how deep in this decision tree I go. And the graph that you get looks like this. And it illustrates an important part of all these machine learning methods. So you can see that as I increase my tree depth, my training data get a higher and higher score. So this keeps rising up, and essentially I'm sort of splitting up my data, and I'm basically designing a decision tree that classifies this particular set of the training data. And if I go to like a depth of 20, I do an amazing job. I get 92% accurate versus a lowly 77 or something like that. But I've held back 40% of my data here. And I also score it. And you'll notice that it rises basically in lockstep here. And then at a depth of about 6 or 7, those two curves diverge. And what this is showing is that I'm starting to overfit the unique set of my training data. And I get better and better there, but I actually get worse performance on my testing data. So you might say, you can decide what the most important results are. You can say, okay, I can pick a depth of around 10 because that corresponds to the peak of the accuracy of my testing data. So about 84, 85% accuracy there. Or you can go a little bit shallower because that's where it doesn't matter what your testing and your training data are doing. So this is the point before which those data points start to diverge. That could be the depth. And so that it'll give you sort of 7 to 10 as how deep you should go. And you'll notice there's not much change in performance for the test over that range. So I illustrate decision trees because they're fairly easy to understand, and they show off this exact behavior, what you see on the screen here. And that's giving you a sense of how to kind of manage using this vast zoo of different classifiers or machine learning methods. In what remains, I kind of want to illustrate two other options. They should use the same techniques where you sort of vary parameters and then test versus train data, but it sort of shows there. And really just go into the scikit-learn manual pages, pick out tests, but use the intuition you get from these sort of single examples as ways of making sure that you're not getting garbage out or you're overfitting your data. Another approach here is what's called k-nearest neighbors classifiers. And the idea here is if I just sort of map, y equals 0 for the galaxy and 1 for a star. This is a somewhat balanced data set. A quarter of the data are stars. We add in our colors, U, G, G, R, R, I, Z. And then for this model, we really need to use a standard scaler. So we scale it down to a common range, and that makes sure that every axis of the data is kind of statistically homogeneous here. And all you do with the k-nearest neighbors classifier is you look at a point in that data space, look at the k-nearest points to that, and then you essentially assign a probability of it being a star at that point as the average number of stars in this ball. So you can basically pick 20 nearest neighbors, 50 nearest neighbors, 5 nearest neighbors, and this can kind of map out the space. So to implement the k-nearest neighbors classifier, you read in the data, you pull out the colors, you create data that are the differences of those colors, you pop out the type, and then you map it onto galaxies. So this is just data setup. We'll use the standard scaler again to get things that have been transformed, subtract off their mean, divide by their standard deviation. We partition the data set, so we keep back 40% of the data randomly from this data set. It's using the test train split method. Then we import the k-neighbors classifier, run it for 10 neighbors, and then you fit the results. And you ask what the testing versus the training data are, and that's around 85%. So a good method that indicates you're not overfitting the data is when your testing and your training lead to the same score. That means that you are roughly in this point before there's a point of divergence. So you want it high, but you want there to be similarity between your testing and your training data. So predicted on stuff that you haven't seen before. So that's basically, it's a quick method. You can just look it up, apply it, and maybe this classifier will work pretty quickly. The next thing or the last method you can sort of reason out is this thing called a neural network. And you've probably heard about neural networks in the context of machine learning. This is essentially machine learning, what we're doing right now. And what we want to do is kind of figure out how to use this neural network method to do the same kind of training. And with the language we've developed, these neural networks are now somewhat tractable. So let's consider a vector of inputs. These are our star brightnesses and our colors. We'll assume that there are n of them. So there's the 5 fluxes and then the 4 differences or the 5 magnitudes and the 4 differences between them. So we'll have a total of 9 input features, and then we'll set up our response variable to be 0 or 1. And what we want to do is we want to make a prediction of my input variable. So I want to map that to be close to 0 or close to 1. And I'm just going to use, for now, a sort of linear-like model where I sum over the k, and we'll call these k elements here a neuron here. And that neuron is going to be some function of my input data times some weight here, and I've used m just to indicate a slope. So essentially we'll take some transform of my input data, we'll weight those transforms, add a coefficient, and we'll get a number that's kind of that maps onto 0 versus 1. So we'll just apply a threshold to this value. If it's larger than that, it's a star. If it's smaller than that, we think it's a galaxy. This h of x is called the neuron in the network, and we can consider this to also be a linear function of weights times the original values in the data plus some offset. And this function g is called an activation function. So right now we have b, m's, and w's as my free parameters in the model. And these are called the weights of a neural network. And you can see that each one of these, this depends on the number of features, and this depends on the number, the W's depend on the number of features, and the M's depend on the number of weights here. So in the case, and so the number of neurons is a free parameter. And we set up this kind of classic graph of a neural network where I have my 9 magnitudes and colors coming in here. And then I'm going to map each of these using the function here to map up to one of these neurons. Then I'm going to do a function on that value, add all of those up, and that's going to combine to give me an output here. So each one of these is accepting from these 9 features. Every one of these contributes to this one neuron up here in the hidden layer. I have some weights that I'm going to pick somehow. And it's just going to be a linear model of the original data and these weights. And I'm going to apply an activation function to them. Some common activation functions are the sigmoid. This is a logistic function. So if it's large and negative, it's 0. Or if z is large and negative, it's 0. If it's large and positive, this function goes to 1, and then it rolls around 0. The other one that's computationally pretty efficient, so the neural network people like this, is called a rectified linear unit, or a ReLU activation function. So if the argument is less than 0, you just return 0. Otherwise, you return the argument of the function. So that can just be the weights here. And if it goes negative, you just floor it at 0. So that means take these inputs, create a linear combination, put that on this hidden layer, apply this activation function, say for ReLU, if it's less than 0, return 0. If it's more than 0, return the sum of the weights. And then I'm going to do that for each of these elements and layers here. I'm going to pick 10 for the number of neurons that I have in my layer. And then I take each of those and I multiply it by some weight, add it up, and then I apply the activation function to this output here. And I say, okay, well, if it's less than 0? If it's less than 0, then I call it a galaxy. Otherwise, it's a star. And so then it pops out and I get a nice result here that takes a vector of colors in, runs through a fixed set of linear combinations and activation functions, and out comes the final result. So that's a neural network. It's actually not too crazy given what we have seen before. Where it starts to get a little crazy is that you don't actually have to have one set of hidden layers. You can have multiple layers here, where here I've picked 5 sets of layers where you basically take the vector in, weights go here, if you transform, they serve as a vector of inputs to another layer, and they are a vector of inputs for our next layer, and it moves through until you finally combine all of the outputs into a single threshold here. So this whole setup establishes this neural network, and all I have to do is tune the model to pick the right values of the weights, the little M's and W's in the model that I had before, and I pick the optimization to provide the best classification on the training data. And you do that just by passing off and say, okay, give me this maximum likelihood per MLP, something perceptron classifier, which takes the number of iterations, which is how many times I'm tuning the weights here. a random state initial. This says I want 5 hidden layers of 10 neurons each. I'm going to use the ReLU activation function. And because I just like to watch my programs tick, I say I want that to be verbose equal to true. Alpha, I believe, is a tuning parameter for how quickly it converges or learns in the machine learning case. You see, it's really just a bunch of linear functions that have really good branding because they made it sound like, oh, neural networks and learning, but it's just, you know, pile of linear algebra. I fit the training data here as fits, takes a few minutes, goes through, and then it reports a score on the testing data and the training data, and they're very close. That's good. So that suggests maybe I could increase the complexity of the model to get good results and make sure I have this similarity between my testing and my training as I tweak the parameters of my neural network. So I wanted to go over that because you hear a lot about neural networks these days, but it's not that wild of a method. Now, there's lots of techniques for actually how to pick the weights properly. There's a lot of free parameters, but the basics are all here encompassed in this single result. So there's a huge number of classification schemes available, but all of them you should treat with the same method. Withhold some data, train, see how you do on the testing data and on the trained results. And I want to stress that if you have stuff in if you're taking your neural network or your k-means classifier and you're applying it out of training data, outside of data that looks like your training data, your warranty is voided. This only works to basically get data that are statistically consistent with the data that the method was trained on. Once you stop doing that and you get out of bounds training, then the methods become a lot sketchier. You have to get a lot more sophisticated. All right, so I hope that gives you some insight as to how we can use classifiers in these results. A lot of classifiers, you can think about them as they can produce vector valued outputs, so you can divide it and say it doesn't have to be a binary classification. Classic example in the machine learning community is recognizing digits from handwriting samples. There it just matches onto 0 to 9 there, so you have 9 possible outputs. So that's really it's a powerful technique once you start vectorizing all of that. But the intuition that we get should sort of guide us throughout this entire process. All right, that's all for now, and I will see you in the next video.